With that introduction to finite number systems, let's talk about what the double class is in MATLAB. It's a finite number system, and here we can describe exactly what numbers it can represent. First, there's 2 to the 52 evenly spaced numbers from 1 to 2 minus 2 to the negative 52, and there's a spacing between them of exactly 2 to the negative 52. I've drawn that below as a interval 1 to 2, closed on the end with the 1 because 1 is represented, and I've drawn it as open on the end with 2 because this list of numbers does not include the number 2. That said, it's not an interval. It's 2 to the 52 evenly spaced numbers in that range. Those numbers can be doubled to give 2 to the 52 more evenly spaced numbers that range from 2 to just less than 4, and so on. We could double that many times. Imagine doing 1,023 separate doublings, and finally we end up with 2 to the 52 evenly spaced numbers from this incredibly large number, 2 to the 1,023, all the way to almost twice that. The spacing between the numbers is 2 to the 971. Rather than double it, we can halve this interval. Having the original interval, which went from 1 to just less than 2, will create numbers that go from 1/2 to just less than 1. Continue doing that and imagine 1,022 halvings. The final result of that will be 2 to the 52 evenly spaced numbers from a very small number, 2 to the negative 1,022, to just less than twice that number. While the spacing is changing from 2 to the negative 52 all the way up to 2 to the 971 down to 2 to the negative 1,074, the relative spacing, the spacing in a given interval divided by the length of that interval, is remaining constant. There's one more set of numbers though, and this is 2 to the 52 evenly spaced numbers from 0 up to just less than 2 to the negative 1,022. These have the same spacing as the most finely spaced interval that was obtained from the halvings. Those are the numbers, then the negatives of all those numbers, and inf and negative inf, and the nada numbers. That is what the double finite number system can represent. An important thing just to reiterate, and I've said it several times, although I've drawn these with spacings that look even across the different colored intervals, the spacing is changing and it's not evenly spaced. The spacing is roughly proportional to the size of the numbers. If you're not conversant in powers of 2, it's useful to describe this again using base 10 numbers, just to give you an idea of how vast this double finite number system is. 2 to the 52 is about 4.5 quadrillion. So here's how we can write this. The double number system has 4.5 times 10 to the 15th, approximately, evenly spaced numbers from 1 to just less than 2, and the spacing between these numbers is about 2.2 times 10 to the negative 16th. Then there are many doublings of that interval, all the way out to 4.5 times 10 to the 15th evenly spaced numbers from approximately 9 times 10 to the 307th to 1.8 times 10 to the 308th. The spacing between those is about 2 times 10 to the 292. There's also halvings of this interval, resulting in 4.5 times 10 to the 15th evenly spaced numbers from this very small number, 2.2 times 10 to the negative 308. The spacing down there is about 5 times 10 to the negative 324th. Finally, there's another 4.5 quadrillion numbers evenly spaced from 0 to 2.22 times 10 to the negative 308th. In addition, there's the negatives of these numbers, and then the special numbers inf, negative inf, and not a number. Again, this line is not evenly spaced. So double is nothing more than a finite number system with quite a few, on the order of 10 to the 18th, representable numbers. Despite its vastness, the simple number 1.4 cannot be represented using this number system. If you start from the number 1 and add multiples of 2 to the negative 52, it will never equal 1.4. In terms of the 64-dimensional array of ones and zeros, the closest representable number to 1.4 is this. We haven't discussed how to interpret these yet. Its value is within about 10 to the minus 16th from 1.4. That makes sense. Remember, the gap between those black lines is about 2 times 10 to the negative 16th. Any number in the red, a real number, should always be within 10 to the minus 16th of a black line. What's going on here is an issue that you've known about all along with your background in arithmetic. A number that has a short or simple description in one base representation may have a long or infinite description in another base representation. For example, 1/3 is very simple to represent in base 3, but it has an infinite repeating representation in base 10, 0.33333. Notice above the repeating nature of the bits in our double representation of 1.4. This should raise a question though. If 1.4 can't be represented, how does MATLAB or any computer convert from a base 10 representation of a number to the nearest double representation? In other words, when we type x equals 1.4, what actually happens, and how does the computer find and assign to x the closest representable number? You can read about the command strtod. That's a low-level command that converts expressions using decimal notation, which really are effectively character arrays, into doubles. There's a nice article I found on the web describing it, and at the end of this module, you'll be in good shape to read that if you're interested. Similarly, for instance, the number 1.78 times 10 to the negative 45th can't be represented exactly in double either, although 178 can be represented. So in this particular example, shifting the decimal in the base 10 representation by 47 places results in a representable number. In any case, the closest representable double to 1.78 times 10 to the negative 45th has a bit pattern like this and is within about 2 times 10 to the negative 61 of 1.78. Again, a relative error of about 1 times 10 to the negative 16. By two examples, we've observed a rule of thumb for a double system of representation, and that's that the maximum representation errors are approximately proportional to the number being represented. The proportionality factor for this bound is about 1 times 10 to the negative 16th.